Thank you for tuning into our presentation on a novel generalization of Diophantine m-tuples over finite fields. I would like to thank YMC for allowing us to present our work, and I'd also like to thank Dr. Kim, Dr. Miller, and Trajan Hammonds for their help with mentoring us and helping out with the presentation. This work was done for the Polymath Junior RU that we did in summer 2021. So first we start off with defining a Diophantine m-tuple in the integers. A Diophantine m-tuple is a set S with m positive integers such that the product of any two plus one is a perfect square for all indices. So here are some examples. First one is due to Fermat, 1, 3, 8, and 120. Euler gave a more generalized formula, which works for any positive integers A and B. We also have a result by Baker and Davenport, which says that given a Diophantine four-tuple or a Diophantine quadruple, given a Diophantine quadruple which contains 1, 3, and 8, it is required that the fourth element be 120, which means that 1, 3, and 8 can only be extended to a Diophantine quadruple in one way. There's also a result which says that in the integers, there are no Diophantine five tuples. So the motivation of this project was to look at Diophantine m-tuples in commutative rings in general, instead of just restricting ourselves to the integers. So Djela and Kazaliki worked on Diophantine m-tuples in finite fields, and they came up with a few results. The first one is the existence of Diophantine m-tuples in Fp for P large enough. They also were able to come up with explicit formulas for the number of Diophantine pairs in Fp. And these formulas depend on the value of P mod 4, the congruence class of P mod 4, and the formulas are on the screen right now. They also came up with an asymptotic formula, which is for the number of Diophantine m-tuples in Fp, and it's P to the m over 2 to the power of m choose 2 times m factorial. So now our generalization, we considered k Diophantine m-tuples, and these are a k Diophantine m-tuple is a set S of m positive integers such that the product of any k distinct elements of the set plus 1 is a perfect square. Now here are a few examples. 2, 3, 4 forms a 3 Diophantine triple. N plus 1, n plus 2, n plus 3 form a 4 Diophantine quadruple. 1, 2, 4, 6 form a 3 Diophantine quadruple in F17. 3, 13, 16, 17, and 21 form a 4 Diophantine quintuple in F23. So as I mentioned earlier, in this presentation, we're mainly concerned with k Diophantine m-tuples over finite fields. So just as a remark, it's actually not a very trivial problem to understand 3 Diophantine triples, or in general k Diophantine m-tuples. It's actually extending a 3 Diophantine triple to a 3 Diophantine quadruple is equivalent to finding intersolutions of the elliptic curve y squared equals abx plus 1 times acx plus 1 times bcx plus 1. So as we can see, for even simple cases of K and M, it's a very complex task, as it is the same complexity as finding integral solutions to an elliptic curve. So since there is no general algorithm to find integral solutions to elliptic curves, there is no general algorithm to find k-Diophantine m-tuples. However, there is a result that tells us that there are only finitely many ways to extend 3-Diophantine triples to 3-Diophantine quadruples. And this was seen in an example earlier where 138, we saw that 138 can only be extended to 138 and 120 as Diophantine 4 tuple in the integers.
So Arjun mentioned a few results found by Duzela and Kazaleki for Diophantine m-tuples in finite fields of the form Fp. So with the aim of finding similar results as them, we tried to answer the following questions. So the first question involves the existence of a k-Diophantine m-tuple for a large N of P. So can we guarantee that? And the second question was if we can find exact number of k-Diophantine m-tuples for various values of k and m, where k is less than or equals to m. And the third question was if we can find an asymptotic formula for the number of k-Diophantine m-tuples where k is fixed. So in our quest to find the first question, to find an answer to the first question, we got the following result. So this is our first theorem. So this theorem basically states that if m greater than k is an integer, then for p satisfying this bound and p being a prime, there will exist at least one k-Diophantine m-tuple in the finite field Fp. So for the proof of this, in this presentation, we will just prove a special case, and the special case is that when k is equal to 3. And the process for finding the proof of the general k is very similar to the special case where k is equals to 3. So the process for proof of k equals to 3 is will give us an idea for the proof of general k. So here's the k equals to 3 case. So this is basically similar to the previous theorem, where we replace the k by k equals 3, and so if p is greater than this bound, then there must exist at least one 3-Diophantine m-tuple in Fp. So, and the core idea of the proof for k equals to 3 and hence for the general k is very similar to what Duzela and Kazaleki did for proving the existence of a Diophantine m-tuple in Fp. And before the proof, we would like to define the following. So we define the Legendre symbol here. So the Legendre symbol denoted as A over P. It is defined as 1 if A is a quadratic residue mod P, and it will be -1 if A is a quadratic non-residue modulo P. And if P divides A, then A over P is 0. Now my friend Kyle is going to talk about the proof.
Thank you. Yeah. So the basic idea of the proof is an induction on M, and relies on this Legendre symbol. For the base case M equals 3, the 3-Diophantine triple mentioned before, 2, 3, 4, exists for P greater than this bound. And now we assume there is a 3-Diophantine m-tuple in Fp for P greater than the bound Dishant mentioned. And we want to show that there's a 3-diophantine m+1 tuple for p greater than the bound when m is sent to m+1. In the proof, we require this. It's helpful to define this G, which is the number of elements of FP where AI, AJ times that element plus 1 over P equals 1. And AI and AJ are just some elements of the 3-diophantine M tuple we assumed. And using the multiplicative inverse and of AI, and the multiplicative nature of the Legendre symbol, we have this equivalent definition here. Now, by an exercise from Finite Fields written by Liedl and Niederreiter, there's actually a bound on G written here. And this bound is helpful, and using this bound and some algebraic manipulation as well as the inductive hypothesis, we eventually get this series of inequalities, which shows that G is greater than m+1, and so there's a 3-diophantine m+1 tuple in FP, namely the elements of the assumed 3-diophantine M tuple, and then attached with appended or by this new X, and X is in FP and is not 0 or any of the other elements of the assumed 3-diophantine M tuple. So as Dishant mentioned before, one of our questions was finding an exact number for the number of k-diophantine M tuples, and we were actually able to solve this for the case of 3-diophantine triples, and it's given by this formula. And as you can see, it depends on the congruence class of P modulo 3, and it depends on this uniquely determined A, where A is congruent to 2 mod 3, and A, as I said, is uniquely determined by this equation P equals A squared plus 3B squared. And actually, to conjecture this formula, we used a program written by Rowan McKee, so we'd like to thank him for his help in our research. And now, before we can go to the proof, however, we need some elementary results from number theory. So the first of these results is what we call a character sum, which is basically just a sum of Legendre symbols. And here we have the linear polynomial ax plus b over p. And it turns out that this sum is, when you sum over x equals 0 to p minus 1, you get 0. And we also need the case when we have instead of linear integral polynomial, we have a quadratic integral polynomial. And we get two cases when if p divides this discriminant b squared minus 4ac, we have p minus 1 times a over p. And otherwise we have minus a over p. We also need this lemma or result by Gauss, and it's basically just a formula for the number of points on the elliptic curve y squared equals x cubed plus 1 over fp. And lastly, we will need a formula or a result that we actually had to find and derive, and it is that the number of distinct triples ABC, where the product ABC plus 1 is congruent to 0 mod p, is we need the number of those triples. And so we have this relation here, depending on the congruence class of P modulo 3. And now I'll just let Lalit handle the proof.
So now we discuss the proof. So basically we start with this equation 12mp is equal to summation of 1 plus abc plus 1 over p prime, where the summation is done over triples abc such that they are non-zero and distinct. And we have this modified Legendre symbol where for a non-zero, a over p prime is just a over p, and for a is equal to 0, a over p prime is 1. So yeah, and the factor 12 on the left-hand side of the equation is just 2 into 6, where 6 is due to the permutations of A, B, and C, and 2 is just due to the extra 1 in the summation. So we can simplify this, and 12mp would come out to be S1 plus S2 plus S3, where we define these three sums in the following way. So S1 is actually easy to evaluate. It will just be P minus 1, P minus 2, P minus 3. And S3 is just the solution of a solution that we obtain in lemma 4. So essentially all we have to calculate to get the result is just the sum S2. So we can use these elementary lemmas 1 and 2, and we can repeatedly simplify the sum S2, and after some simplifications, we would get minus of P minus 1, P minus 4 plus 2 times summation of CQ plus 1 over P over non-zero C. And using lemma 3, we can also evaluate this sum. And in particular, we would get this 2a minus 1, where when P is congruent to 1 mod 3, and minus 1 when P is congruent to 2 mod 3. Essentially, the CQ plus 1 over P, this summation, if C runs through all the elements of FP, is going to be the error term 2a, which you can see in the lemma 3, in the statement of lemma 3. So when you remove the case where C is equal to 0, that would just give 2a minus 1. And since the error term is not there, for P congruent to 2, you will just get minus 1. And of course, you can just now write MP as S1 plus S2 plus S3 divided by 12, and it would give this really nice formula. So what about the future? So there are a lot of directions to go in now. And so specifically with finite fields, you can try thinking about number of Diophantine quadruples or 5 Diophantine quintuples, and you can generalize it to like a higher case, other integers, other positive integers k. And you can also try finding formula for 3 Diophantine quadruples, which is probably a bit more difficult due to because of the fact that you'll have product of Legendre symbols and that. You can generalize that to k Diophantine k plus 1 tuples. And of course, one thing that we would like to do is find an asymptotic formula for k Diophantine m tuples in FP. And the choice of finite fields is just arbitrary. We just wanted to like maybe find nice formulas, but you can easily consider this generalization over other commutative rings with unity, for example, integers and rational numbers. And you can read about these other generalizations that other people have considered, which are really popular. So you can consider k Diophantine m tuples with property dn, or you can consider the product to be 1 less than a square or some higher power. You can read about these generalizations on Andre Dujela's website. Yeah. Okay. So these are some of the references that some of the main references that we used. Okay, thank you for your time.